Good afternoon, everyone. Welcome back. Hope you had a good lunch. And welcome to our afternoon session, which is really talking about really the use of digitalization related to asset management. I'm very pleased that we have Fulvio Rovetta from Emerson. Fulvio is joining us all the way from just outside Genoa in Italy. So we have a pretty international group, as you'll find out later this afternoon. So very pleased to have Fulvio. He's a real expert in this area around using data and analytics to improve equipment performance, particularly around rotating equipment, which you all have. So very, very interesting. And again, complementary to everything that we've had already today. So very welcome to you, Fulvio. I'll see you at the end of the presentation. Okay.
Okay. So sorry, I cannot find the button. Oh.
Okay. Mark, have you found it?
No, not yet.
The screen sharing button.
Screen share. Okay.
You see it?
Oh yes. Sorry.
Mark, he's looking for the screen sharing button.
It's on the bottom part of your toolbar, Fulvio. Yeah. Just along from your microphone mute button and your camera button.
Yeah, the next one.
It's screen share.
TV scroll. You see it says screen share? Yeah.
I think he's found
it.
Brilliant. Yeah. Brilliant. Bye.
The wrong presentation, but I'm coming. I mean. How it should work. Can you see?
Fulvio, yes, we can see. Yes, we can see.
Okay, good.
No problem. We'll leave you to it.
Thank you. So, good afternoon. My name is Fulvio Rovetta, and I'm talking about analytics and how it can help us to maximize the equipment performance. This is a quick agenda. So basically, we are going to see what is analytics and how we can use it for our assets and some case histories. My company is Emerson. It's a company founded 130 years ago with 88,000 employees, split in two main business platforms. I belong to the automation solutions platform, and annual revenue is last year was $18 billion. We can provide solutions in the field device world, control systems, and data management. And in data management, we have a platform called Plant Web Optics Analytics that is for advanced analytics. Of analytics, we see that it's a way to use historical data, and we have plenty of historical data in data lakes, historians, control systems, databases, and we need to use them to do discoveries, to interpret what happened, and communicate to the stakeholders to support the decision-making process. And we can recognize four different types of analytics, starting from the descriptive analytics that tells us what happened. The diagnostic can tell us why it happened. And here we are still in the reactive mode. We cannot change the future. While with the predictive analytics, we can say what is likely to happen. And better, with the prescriptive, the analytics can tell us what action to take in order to face what is likely to happen. So, analytics is very powerful. It is considered as one of the top drivers for digital transformation. Artificial intelligence and advanced analytics, we'll see, they are very, very strictly connected. And consultants estimated as over $4 trillion per year, the growth in industrial manufacturing for what concerned by analytics. But customers very often are still confused. They don't know where to start from, what are the tools they have to use, the models, and the type of problems they can focus, because they feel that very often there is a kind of oversold with analytics. It's proposed as a kind of magic, but actually it's not magic. And in addition, if we look at the landscape, we can count about 1,000 different solutions for analytics. So this makes things more complex, but Emerson, to simplify, did a choice. So we are focused on operational analytics, and operational analytics is focused. So we are looking at the production world, the real-time world, and trying to get the value out of that. And how we can use analytics in this area. Basically, we identify two main families: the principle-driven analytics and the data-driven analytics. For principle-driven, we are using the traditional tools. So first principles, equation, laws coming from thermodynamics and physical, and the rule-based. The rule-based, we are not using equations, but we are using domain expertise. This is what we do, for instance, with the failure mode effect analysis. The other big family is the data-driven analytics. Here we have no equations, no specific domain knowledge, but we have historical data. So we use historical data to build statistical models, or leveraging artificial intelligence and machine learning, we can build black boxes as neural networks able to predict values and identify patterns. And where we can apply the operational analytics, almost everywhere, but to be more focused, we identified four main areas. The first one is the production. Analytics can help us to improve the quality of the product, to improve the process, avoiding abnormal conditions and preventing failures, slowdowns and shutdowns in the plant. Can also help with the reliability and safety, because it can help to predict the health of all the equipment, and also supporting maintenance, moving from a reactive maintenance to a predictive maintenance. And this impacts also on safety, because we reduce the possibility of a major incident on our equipment. And the last area that is very important is about energy and emission. To pinpoint the equipment or the plant units that are bringing issues with energy consumption, explaining why they are doing that and how we can fix the problem. And this also has impact on emissions, so we can make more efficient use of energy and reduce the emissions. So how can I use such a technology for my assets? We use an example that comes from our experience, that is a compressor. Compressors are basically everywhere. They can bring with them serious issues in case of a failure related to safety, to financial or business losses, and also impact on the environment. So typical customer pains ranges from avoiding safety incidents, of course, staying respectful of regulations and for what concerns environment, and quickly detect and identify problems in order also to improve the maintenance, reduce maintenance cost, and obtaining peak performance, so improving the performance, not only for critical compressors, but also for smaller compressors that very often are not monitored. So for these small compressors, the idea is to provide a library common process equipment that includes not only compressors but also turbines, heat exchangers, pumps, and all the typical equipment. And they are templates that can be used just connected to the input and the output as minor tuning, and they can provide us performance insights and knowledge that can be immediately used to action. And the library can be also customized, so the customer is able to modify the templates to adapt to specific case. The principle is very, very easy. In this case, we are just using first principle models. First principle models for calculating case used and sent to a module for event generation using real-time data to generate notification, to inform the operator that something is not doing in the best way. That's a typical fault matrix for a reciprocating compressor. You see that you need just about 10 input tags to get a large number of information that are immediately calculated and made available. And the result is presented on a web interface that can show you at the plant level what is happening, so providing you a summary, an overview of what all can drill down and see the specific equipment, which is the health and performance index, problems with the sensors, and if you have some problems, it will be shown near in this picture near the area where the problem was found. So this is the basic solution, but then you can extend it. Extending it means adding the data-driven component. So in this case, what we need historical data. Historical data are processed offline with a dedicated tool that is the Modeling Studio. And then the outcome of this analysis is a model that is put on online. It receives real-time data and provides calculation, KPIs and other calculations that are sent to the event generation together with the first principle and the real-time data. The results from the event generation module is notifications, and notifications are also sent to this root cause analysis module. Here, the root cause analysis is performed. So if the problem that it was found is at a low level, I mean a valve that gets stuck, it can have some impact on my equipment and on the process. So this module is able to predict the impact of a problem at higher level until the compressor fault. Vice versa, if I have the event is already happened, like the compressor shut down unexpectedly, this module helps the user to find the root cause, so to pinpoint the responsible of a failure and guiding in fixing the problem. The example I want to show you is about a reciprocating compressor with 4 throws. That's a real case we had with a customer. The customer wanted to run a proof of concept to have us demonstrating the capability of our system to find problems without knowing almost anything about the story of a system. So they gave us the historical data, the P&Is, tag descriptions and mapping with the P&IDs, but they didn't tell us anything about the normal operation periods, the failure history, and the trip tags. So we had to find everything just using historical data. So what we did, the first step was cleaning the data, identifying the shutdown periods, and finding which shutdown periods were real planned shutdowns and which other were due to a failure. This was done using the tools that are available in the Modeling Studio. And then next step, identifying a data set that would be useful to train the model. We run the training of the model. This model is predicting the throw sea temperature. So it is using indirect measurement to predict the output. And this is the first step. So the system using machine learning is creating a model that is able to map the training data. So the error is pretty low, so the model is good quality, and we tested it with new data, so data that were never used before. And here you have to demonstrate that you are able to predict the temperature with reduced error, and this is the case. At this point, we have a model that is able to predict the temperature when the compressor is working in a correct way. So this is the theoretical temperature that we should get. And we built an health index. The health index is MTR, minimum temperature ratio. That is the minimum ratio between the expected temperature versus the actual temperature for each throw. So we had 4 throws. We implemented 4 models, as the one we have seen. And the model is deployed by drag and drop in this environment. This is the graphical block language that is used to program the application. And here, this rule is implementing exactly this formula. So for each throw, we compare the expected value with the value coming from the control system. And the other block selects the minimum value. So this is the KPI we are using for health, but the same model is used also to generate an event that is the high temperature. So here we are using the model that we developed before. We are comparing against the actual temperature. When the ratio goes below 0.98, it is generated an event. This event can be sent as a notification to the operator, so he knows that there's something going on, but it's not very useful because in this way you are flooding operators with lots of alarms. So in this case, this notification is sent to this fault tree. This is another environment. This is the root cause analysis module. Again, we are programming graphically. We are building this big fault trees that can be also imported from existing FMEA tables. And let's zoom a bit. What happens here? Here we have the notification. The notification changes the status of this block, moving to red. This means that it's active. This problem is currently active. The analysis is moving on the fault tree to the next block connected to this one, and this tells us that having a problem with the discharge temperature high in the future, it can bring to a compressor failure. So we are going to inform the operator that, and this is the user interface, the operator will know that there's a problem, there is an active root cause, this is the impact of a root cause, and this is the corrective action. So in this way, at any time when an event is recognized, the operator will be immediately informed, but at a higher level, not just receiving hundreds of alarms that are difficult to be understood. In this way, it just received essential information that can bring him to fix the problem. And the results were tested over the historical data. So there was a playback of historical data, and we could demonstrate that the event was identified twice before a major shutdown. So following the instruction of the analytics program, they could have fixed the issue and avoided this shutdown with 6 days in ahead. So a couple of other case studies. This is a chemical plant. We had a propane refrigeration train where 6 compressors that had a lot of problems with surge. In this case, the customer asked us to focus on surge events. We developed a number of things around that, and also the LT index here was the distance from the event, the surge point, and we are guiding the operator in staying away from the surge point, and also monitoring other problems on the compressor. And this was completed and is running since more than one year. Allowed the customer to decrease downtime with early detection, to reduce the cycle from the detection of an issue to the resolution, and also the effort to manually analyze data coming from different sources and doing the diagnosis, because everything was made automatic. That can monitor worldwide their refrigeration train. The other one is in oil and gas, is onshore facility in Russia. The customer had serious incidents with major rotating equipment. They wanted us to monitor compressors and turbines. It was a pilot project for 4 or 5 equipment, and the scope was to prevent unplanned shutdown and to reduce maintenance cost, extending the maintenance time from one event to the other. So moving basically to a predictive maintenance mode. And in this case, we were able to identify predictively the problems. We improved the reliability and safety. And now the customer is extending the application to their whole fleet of critical equipment. So to conclude, we can summarize what we discussed. We see there's a need to leverage the huge amount of available data. Data analytics can help us unlocking large saving opportunities. And if we go to the operational analytics, we focus on production where we have the highest values that can be found. And combining first principle, data-driven and rules really empowers analytics, gives you more powerful tools. So with these tools, you can apply them to the operations and achieve good results and return on investment. So that's all.
Okay, thank you very much, Fulvio. As I say, if you have any questions, please ask separately Fulvio, and we think that Fulvio is now going to be able to join us for the Q&A as well, which is great. But yeah, questions very welcome, very professional, very important area. And again, as I say, we've tried to cover most areas. We've done inspections, control equipment, installation, decommissioning, rotating equipment, lean, TPM. But we're continuing now. To be honest, this is an area that Emerson could have talked about, but we've got Fraser Nash. So if you go on to the next, thank you very much, Fulvio. And if you want to go on to the next presentation from Chris Jones of Fraser Nash, I'll see you there. Thank you.
Thank you.